This poster is about an extension of the superreconciliation method to take into account horizontal gene transfers. The evolution of some genomic regions can be traced back to a shared ancestral region. We call such parts of the genome synthenies. Gene families that are located in such synthenies do not evolve independently from each other. This relationship must be taken into account when we want to reconstruct the history of syntheny families. Superreconciliation is a method designed to reconstruct the history of synthenies through segmental gain and loss events. Existing algorithms for computing superreconciliations focus on the duplication and loss setting, either with unlimited or without any gene rearrangements. The DL setting ignores important evolutionary mechanisms such as horizontal gene transfers, or HGTs, and tandem duplications. HGTs in particular are essential to the study of the evolution of operants in bacteria. So how can we extend the superreconciliation method to infer HGTs? In the superreconciliation problem, we are given two trees, a syntheny tree and a species tree. The syntheny tree is a phylogenetic tree of the synthenies that make up the family that we want to study. Each one of the extant synthenies belong to a species of the species tree on the right. What we want in the output is a labeling of the internal nodes of the syntheny tree with both events and ancestral synthenies. And we wish to find such labelings that minimize the number of non-speciation events and the number of segmental loss from one ancestral syntheny to the other. The first part of the superreconciliation is an event labeling. This labeling corresponds to a mapping of the syntheny tree onto the species tree. In the DL setting, where only speciations, duplications, and full losses are allowed, the only solution that minimizes the number of non-speciation events is obtained via LCA mapping, and the LCA mapping can be computed in O of n operations. N is the number of nodes in the syntheny tree. So here on the left of the figure is the LCA mapping of the input. We get a solution with a cost of 3, with 2 duplications and 1 full loss. Now if we allow HGTs, things get a bit more complicated, because now there may be more than one solution, and LCA mapping is not always even part of this solution set. In the figure on the right is an example of an optimal event labeling. This one has a cost of 2 because it has 1 duplication and 1 HGT. If we want to find solutions, we need to scan all possible mappings. This can be done in time O of nm, where m is the number of nodes in the species tree, using an algorithm from Bansal et al. Now the second part is to find a syntheny labeling of the syntheny tree. We wish to assign to each of the ancestral nodes an ancestral syntheny, and such an assignment will imply segmental losses where some parts of the syntheny are lost. Of course, we want to find a labeling that minimizes the number of such losses. We have two versions of the problem. The first one is the ordered version. In the ordered version, rearrangements are forbidden, and any two pairs of gene families must keep the same relative order throughout the evolution. Computing a labeling that minimizes the number of such losses is an NP-complete problem that can be solved in O of n times t times 2 to the t log t plus t, with t the number of gene families in the syntheny. Here on this example we have two losses that are located on the edge from the root to the right child. In the unordered version, rearrangements are allowed, but are not minimized, so we can have any number of rearrangements. Note, for example, that the lower right syntheny has a different order on the gene families D and B relative to the other synthenies. As a consequence of allowing any number of rearrangements, we can have at most one segmental loss on each edge, and this makes the problem much simpler. Indeed, a solution that minimizes the number of segmental losses can be found in O of n times t operations. Now, if we know how to minimize both labelings independently, how can we move to a solution that minimizes both ports at once? If we have no HGTs in the DL setting, this is simple. By minimizing each port sequentially, we actually get an optimal solution. But when we allow HGTs, this property doesn't hold anymore. Look at the example on the right. These are two superreconciliations from the same input. The left solution is the one obtained by sequential optimization. First, we minimize the number of events, and then we found an ancestral labeling to minimize the number of losses. The global cost is 5. But on the right, we did something a bit smarter. We added one event in the first part, but this allowed us to save 2 losses. So globally, we have a cost of 4, that is strictly less relative to the first one. So if we want to find a globally optimal solution, we need to go through all combinations of the two parts. This can be done with dynamic programming. And in the ordered version, we get an algorithm in time O of n times m squared times t times 2 to the t log t plus t, while in the ordered version, we get an algorithm in time O of n m squared t. Now that we have algorithms for the HGT extension of superreconciliation, we can move forward to future work on this method. The first one will be to validate the model with simulations. We want to make sure that adding the HGT possibility gives us more accurate reconstruction of histories. We are also working on an application of the superreconciliation with HGT to real-world evolution studies. And of course, the extension work is not done because there are still more evolutionary mechanisms that are not taken into account. For example, tandem duplications or gene gains, whereby new gene families can appear during the evolution of a synteny.